Let x be the random variable representing the number of students in a group of size k. Now we can write x as the sum of indicator random variables. Let's call them I1 up to In, where II is 1 if student I is in a group of size k. And 0 otherwise. And we want to compute the expectation of x. Now, using the linearity of expectation, we have that the expectation of x is equal to the expectation of I1 plus the expectation of I2 all the way up to the expectation of In. Now, the expected value of an indicator random variable is just the probability that the indicator random variable is equal to 1. And from the previous part, we know that the probability that a particular student is in a group of size k is just 1 over n. So we have 1 over n plus 1 over n plus 1 over n. We have n of these. So therefore the expectation is just 1. Let y be the random variable representing the number of groups of size k. Now, if x is the number of students in a group of size k, then it is easy to see that y is just equal to 1 over k times x. Now, the expectation of y is going to be 1 over k times the expectation of x by the linearity of expectation. And from the previous part, we computed that the expectation of x is just 1. So therefore, the expectation of y is just 1 over k. The crucial observation in this problem is that there can only be at most one group with more than half the students. So that means we can write the probability of a group of more than half is just the expectation of some indicator random variable z, where z represents the number of groups of size greater than n over 2. Now we can write z as the sum of more indicator random variables. Call them zk, where k is between n over 2 and n, where zk is the number of groups of size k. So then the expectation of z is just going to be the sum of the expectations of the zk. But since each of the zk's are indicator random variables, we have that this is just the sum of the probabilities that they're equal to 1. And from the previous problem, we know that these probabilities are 1 over k. Now in terms of the harmonics sequence, we can write this as hn minus hn over 2 if n is even. Otherwise, it's hn minus h floor n over 2. So in the previous part, we got the expressions hn minus hn over 2 for n even, and hn minus h floor of n over 2 for n odd. So plugging in the approximation, h of n is approximately ln of n plus gamma. We have that this is just ln of n plus gamma minus ln of n over 2 plus gamma. And simplifying gives us ln of n minus ln of n plus ln of 2, which is just ln of 2. Floor of n over 2 for n odd is just n minus 1 over 2. Plugging in the approximation here, we have that this is approximately equal to ln of n plus gamma minus ln of n minus 1 over 2 plus gamma. The gammas cancel as before, and we're left with ln of n minus ln of n minus 1 plus ln of 2. Now we can simplify these first two terms a little bit by writing ln of n over n minus 1 plus ln of 2. Now as n approaches infinity, n over n minus 1 approaches 1. So this is approximately equal to ln of 1 plus ln of 2. And ln of 1 is just 0. So we're just left with ln of 2. So regardless of whether or not n is even or odd, we have that the sum approaches ln of 2.